Hey guys, welcome to Safi Mixed. In this video, I want to find the solution to Schrodinger wave equation in the presence of finite square with potential and would like to study the behavior of the eigenfunctions of the problem. And I would like to kick off by writing the mathematical form of the finite square with potential. A finite square with potential is written Vx in the form of this conditional statement minus V naught minus A lesser than X lesser than A, and then 0 elsewhere. Elsewhere mean it is 0 for X lesser than minus A and X greater than A. And if I want to represent the geometry of this potential, it would go something like this. And look, here we are taking x, that is v depends only on one dimension, and we take that one dimension along x-axis, and from here we see that x is the boundary of the potential at minus a and plus a, means that the coordinate, that the origin of coordinate x is falling on the middle or on the mid of the potential. That is, if I want to represent the origin of a coordinate system, this point would be minus a and this would be a. And we are taking our coordinate system in such a way that the vertical line represents Vx, that is the potential in one dimension, and this exactly at this level is the origin of our coordinate system. So in the downward direction, the upward direction, v increases, it is positive, and from this downward v is negative. So at this position the potential is minus v naught as described over here, and this is at this position, this is the origin. So at this position x is 0, x is equal to 0. To the right we have positive value, and the positive value we represent with a, that is one boundary is at a and the other boundary is on minus a. And now obviously this potential splits the whole space into three regions. One, this region where the potential is 0 from x lesser than minus a, to this side it is 0 from x greater than a. This is, I call this third region, again potential is 0, and I call this second region. So the potential in this region is given by this minus v naught. And if we look into this situation, we again have two different types of problem. If the total energy of the particle is lesser than 0, that is E is lesser than 0, then obviously this is a bound particle. And if the total energy of the particle is greater than 0, it is positive, that is we have this condition E greater than 0, then this is just a scattering problem. So the square root potential gives us two different perspectives. One, we can use the square root potential to describe bound states, and the other we can use square root potential to understand scattering states of the particle for E either greater than 0 or E lesser than 0. Now in this particular video we will talk about this condition, that we will solve the problem for E lesser than 0, that E would be negative. So E lesser than 0 will take total energy as negative. And if you look in the literature, there is another description of the potential in which if I want to write it down, it goes like this: v prime of x equal to 0 for minus a lesser than x lesser than a, and is plus v naught elsewhere. However, these two potentials are trivially connected with each other. These two descriptions or these two geometries are trivially connected by an equation like this. We can write Vx equals v prime x minus v naught. For example, if I consider the values of v naught, I can obtain from this equation the values of v. When v x naught is 0, that is we are in this region, this equation gives minus v naught, which is this thing. And when v prime x is equal to v naught, so v naught minus v naught is 0 in this region, so that gives us 0. And similarly, if we invert this equation, we can write v prime of x equals v of x plus v naught. Now, putting the value of v of x, we obtain the values of v prime of x. So the two description of the potentials are trivially connected with each other. Therefore, the observable physics, whether we use this or this, would remain unchanged. So it doesn't make any difference whether you use this one form or this one form. The net result of this of the wave functions and of the energy spectrum would remain unchanged, and therefore we stick to this form and would drop this one form. And while we want to solve our problem for this form of the potential and for E lesser than 0, this is the condition. I'll talk about this in the next lecture, but for the time being we want to do like this. So we want to solve Schrodinger wave equation minus h bar squared divided by 2m. And there is one more thing. Since this potential is time independent, therefore we can use the time independent Schrodinger equation to find the wave function, because the time dependency then goes to a global phase, and that we are not interested in that. So this is in fact a solution to stationary wave functions. And we know that the Schrodinger wave equation is given by d squared psi of x over dx squared plus v of x psi of x equals e psi of x. And now I want to use the description of the potential, the form of the potential, to solve Schrodinger wave equation for first region, second, and third. And I begin to solve it for first region. And in the first region, E, and for this E is negative. In the first region, V is 0 from these conditions we see. So, and I represent the wave function with subscript 1. So I can write the Schrodinger wave equation for region 1 with condition that x is lesser than minus a for this condition. So the Schrodinger wave equation for this condition becomes minus h bar squared divided by 2m d squared. I'll put a subscript 1 with the wave function and dx squared. Potential is 0 in this region, so I set this term equal to 0, and that gives me E equals psi of x. I can drop this sign to put a negative sign over here, and I can take these parameters. I multiplied the whole of equation with the inverse of this to write the equation in the form d squared psi 1 of x divided by dx squared equals minus 2m e divided by h bar squared. Here is psi 1, oh, not that one. Here is psi 1, right? And then psi 1 of x. Now look, this is a constant factor with the wave function. E is constant, m, h bar, everything is constant. So I want to define another constant, and I'll call that energy parameter, because if I define it like this, I want to write this over here. I call that parameter k, and can write this as minus 2 me divided by h bar squared. Now look, energy is lesser than 0 means E is negative. The negative of E multiplies with this negative makes this whole thing positive. And the square root of positive integer is real. So therefore k is positive and real. And we will use these properties of k later on. So you should memorize that k is positive and k is real. And I'm writing this over here because I'll be using this later on. So k is a positive real, therefore, and I take this to write the equation in this form: psi 1 of x dx squared. This whole thing is k squared, and I'm taking that k squared to this side. It becomes minus k squared, and I write this as psi 1 of x equals 0. And this is a well-known second order differential equation. You may have seen such equations repeatedly in your classical mechanics and other courses. Therefore, the solution to this differential equation, I will need to find the roots of the equation. In the roots equation for them, I can write d squared minus k squared equals 0. This implies that d squared equals k squared, or this implies that I write this over here, d equals plus minus k. So the Schrodinger wave equation in region 1 has two roots. And from the solutions of second order differential equations, we know that every root corresponds to, that every root of the differential equation corresponds to an exponential solution. So therefore we have two solutions. One corresponds to positive value of k and the other to negative value. So that means I can write the solution of psi 1x in this region as psi 1 of x is in fact equal to a exponent minus k x plus b exponent plus kx. Yeah, this is from superposition principle, but we need to look this equation, evaluate this equation, examine this equation with respect to another property of the wave function. We know that the wave function, in order to validate probabilities, must always be finite. And with that approach, if I look into this factor, since x is negative in this direction, this factor goes to infinity when I set x equal to minus infinity. That is, the first term on the right of this solution goes like this, minus k, and since when I go to infinity, the value of x is minus, therefore I put minus infinity over here. Or in other words, let me write when x goes to this term goes to infinity, when x goes to x goes to minus infinity. That is, if I replace x equal to minus infinity, this gives me minus k into minus infinity equals exponent k infinity, and therefore this goes to infinity. So this means the wave function, due to this factor, diverges, and a diverging wave function is not physically acceptable. Therefore, we conclude that the integration constant, the undetermined constant a in this equation must be 0. So I set a equals 0. Then I can write psi 1x in the form psi 1 of x equals b times exponent kx. But keep in mind, this is valid for what? X lesser than minus a. So in order to visualize that negative sign of the value of x, I can write this equation into another form. I put this into the form exponent minus k and x. So the exponent will always be negative, whatever the value of x may be. So I put x inside the absolute and extract that negative sign over here. And I want to note this equation in the first region. So our final solution in the first region is this: psi 1 of x equals b times exponent minus k into x. And still b is unknown to us. We will find its value, that is the constant of integration in the second derivative, and we would obtain that from the boundary conditions on the wave function. So we have on this solution, and this solution is valid in the region x lesser than minus a, right? I inbox this like this. This is one solution. So I don't need any of these things. Therefore, I remove them now and want to find the wave function in region 2. for the Schrodinger wave from the Schrodinger wave equation, and I represent the wave function in this region with subscript 2. So I change the region now to this, that is region I want to solve this for D with a minus a lesser than x lesser than a, this one. So for that I'll get minus h bar squared divided by 2m d squared psi 2 of x divided by dx squared, and the potential is negative, so I put the value v naught and it's constant as well, so I write this as psi 2 of x equals e psi 2 of x. I take this term to this side, so it would become minus, and then taking the minus common from these two terms, I can put the equation in the form minus h bar squared divided by 2m d squared psi 2x divided by dx squared minus v naught plus e psi 2x equals 0. And now I want to multiply with the inverse of this thing with both terms, and I can cancel this minus sign, so it is this plus, and can finally write the equation into d squared psi 2 of x over dx squared plus 2m into v naught plus e divided by h bar squared into psi 2 of x equals 0. Again, if we look at this, E is constant, V naught is constant, everything is constant. Therefore, I can define another constant parameter of energy depending on energy. And I denote that with Q to write it like this. Q equals 2m into V naught plus E divided by h bar square, the whole square root. Again, Q is the energy parameter. So K is energy parameter, Q is energy parameter, Q is the energy parameter within the well, and K is to this side of the equation. So with that value, I can write this equation in the form d squared psi 2 of x over dx squared plus, it will become q squared psi 2 of x equals 0. And the roots equation for this differential equation becomes d squared plus q squared equals 0. This implies that d squared equals minus q squared, and if I take the square root, I can write d equals plus minus iota q. So again, since this is second order differential equation, we have two roots, but this time both the roots are complex. We have an iota over here, and again there could be two solutions, and I want to write those solutions here. So the solution in region 2, which I write as psi 2x, is in fact given by c times exponent minus iota qx, right, for the minus value, and then plus d exponent plus iota qx, and this is obviously for this region. So let me write the region as well, minus a lesser than x lesser than a. So this is the solution of Schrodinger wave equation, or this is the wave function describing the behavior of the particle within this well. And again, C and D are undetermined constants that we can describe their values. We can find their values from boundary conditions on the wave function and on its derivative. So this is the solution to Schrodinger wave equation in the within the well. Within this region described by these values of x. Now I can solve Schrodinger wave equation in this region, and in that region what will I do? I will write this equation in the form, I'll just put this as 3, I call that 3, and in that region v is 0, so this term would vanishes, and I'll be left with an equation like this: E psi 3x, right? And it is the same equation like we solved for this region, but the only difference is that now x has positive values. And for that, I can define again k with these values exactly because e is negative, so it would again be a positive constant. And if I solve this, I'll get two roots from this, and those roots would be of the form like the same we had that. So we will get two roots from the equation d is equal to plus minus k, and for every root I have a solution. Therefore the solution side 3 I would write like this: side 3x equals d, so I write e exponent minus kx plus f exponent plus kx. And again, we need to evaluate this function from the perspective of the behavior of wave function. The wave function must be finite, but this time x appearing in the argument of the two exponents is positive. And when x is positive, if we look into this function, then when x tends to infinity, this function, that is exponent k of infinity, goes to infinity. So that blows up the wave function, that diverges the wave function. That means this part of the total wave function is not acceptable. That violates the probability of finding the particle. So that means the integration constant f in this term should be 0. We set this equal to 0, and then we have only the single term. Therefore I note this equation here, and I write side 3 of x is equal to e exponent minus kx, and this is for the region x greater than plus a. So now we have the wave functions in all the three regions of the space, and if we know about the wave function, that means we can further analyze the behavior of the particle. And obviously, if we know the wave function, next we need to find the eigenfunctions. We need to find the eigenspectrum, that is eigenvalues corresponding to these wave functions. And I would like to do that in the next part of the video, so don't go anywhere. And I'm adding and the next video is and the link to the next video is in the description, so click on the description and watch the video what we have next.